Hey folks, this video is going to be an introduction to the energy unit. We're going to talk about mechanical energy today. And so we'll start with our definition of energy. They're going to be very vague terms. Energy is something that transcends all science courses, and that's a lot of okay. So energy is defined as a scalar quantity, meaning it just has a magnitude, it's not associated with any direction, that describes the state something is in. And so I'll talk about that in a minute. The state of an object or system. So when we say scalar, we mean something that just has magnitude. When we say the state of something, we mean any sort of description of what its condition is. It can be temperature, velocity, mass, location, arrangement, orientation, temperature. I said temperature already. So there's lots of different ways to describe the state of something. An object is a single thing, and then a system is a collection of objects. And so one of the things that you'll do in this course, in this unit specifically, is you'll get a lot of practice identifying the system you are analyzing, and that is going to define what is in the system and what is outside of it. The other way to define energy is it is the ability to do work. Now, before we talk about mechanical work, we'll just think of it as the ability to do things. The more energy you possess, the more things you can do. So that if you haven't eaten a lot on a particular day, you're going to have a hard time like shoveling snow later that day. So you eat to get energy, and that energy allows you to do things. The unit of energy that carries through every form of energy that we talk about is the joule, abbreviated capital J. The joule is defined as a kilogram meter squared per second squared. And so you will see this pop up in equations. If you do dimensional analysis on any equations, you'll start to see these units are always appearing whenever something is in joules. So there's lots of different types of energy, and we are going to focus today on two types of energy and one category of energy. The first type of energy we're going to focus on is kinetic. And that is energy due to motion. Motion itself is not a variable, and so according to Newton and people who use Newton's second law to figure out things about energy, motion is described by a couple of variables. And so in the world of kinetic energy, there are three things that something can do to have energy. It can translate, meaning it can move from place to place. It can rotate, spinning around a central axis, and it can vibrate. And so if you think about bonds in the water molecule, the hydrogen and oxygen atoms aren't a fixed distance away from the bond, kind of jiggles a little bit, and so that's the vibrational motion. So we are going to focus today on translational kinetic energy. We will learn about rotational kinetic energy later, not really learn about vibrational kinetic energy. So the equation for translational kinetic energy is 1/2 mv squared. So K is the kinetic energy, and then m is the mass, and v is the speed. So kinetic energy, like all forms of energy, is a scalar quantity, and so it relies on the scalar quantities of mass and speed. The faster something's going, the more kinetic energy it has, and the more mass it has, the more it could have kinetic energy. To give you a quick example of kinetic energy, we've talked about projectile motion before. And so if we have a flat field and maybe a soccer ball gets kicked, the soccer ball gets kicked up in the air and it comes back down. So if we analyze the flight of a projectile, we would say things like, the person kicks the ball to give it kinetic energy. As it is on the way up, maybe from here to here, we would say that kinetic energy is decreasing. Because we've studied the idea that as a projectile climbs to a greater height, it actually slows down. Its vertical velocity gets closer and closer to zero. And so on the way up, the kinetic energy of this ball is decreasing. The other way to think of this, which will become more important later, is that this ball, the way it's moving, is it's moving against gravity. The direction of its motion is generally like up and to the right, and gravity is straight down. And so gravity is going to pull on it to slow it down. Now, on the way down, we would say that k is increasing. So for all the reasons why it was decreasing on the way up, it is increasing on the way down. And so, its vertical velocity goes from 0 to bigger negative numbers, so it's actually speeding up as it's coming down. It is now moving in the same or similar direction to gravity. So we'll work with the equation itself in another lesson, but in general, if something's speeding up, its kinetic energy is increasing, slowing down, the kinetic energy is decreasing. There will be another type of kinetic energy in a future unit, but for now, we are going to talk about gravitational potential energy. And so potential energy is stored energy. And so you've probably studied kinetic and potential energy before. But energy that is stored has the ability or potential to be used for something. And so you can store energy with gravity. So this is energy that is stored due to a gravitational attraction. And so I want you to start to think in terms of stored energy versus energy that is being used, and the release of energy. So if you have something in your hand and you move it to a different location, you can actually store additional energy in it due to gravity. Depending on where you put it, you can store that energy, and then you can use that energy to have the object do something. And so once we get the equation, we'll think about that. So gravitational potential energy has the following equation. I am probably not going to use it exactly like this in the equations that we complete, but this is the official equation from your equation sheet. So the variable for potential energy is the capital letter U. That's we think of the letter U is used to describe internal energy of something. So when we talk about potential energy, we're always going to talk about systems of objects, and we'll talk about that more later. But storing energy in gravity means you're storing energy between essentially the planet Earth and something else. The delta is there because it is up to you, the physicist, to define where zero potential energy is. And so I will give you an example of that. So this is the gravitational potential energy relative to a reference point where y equals 0 and UG equals 0. So you have to, when you use this equation, you have to decide where this reference point is. And so my example to you is, if you are, this is going to be an awful picture, but if you are in RMHS, RMHS is obviously on the ground. But if you are in physics class, then you are standing in room 314, and your head is sticking out of the roof of the building. You are enormous, and you are standing some height above the ground. And let's say you're holding like a tennis ball. So here's your tennis ball. Well, you have a choice to make. If you want to describe the gravitational potential energy of the tennis ball, you need to know its mass. You need to know the strength of the gravitational field, 9.8 newtons per kilogram. And you need to know how far away you are from the reference point you choose. And you are choosing a point where the gravitational potential energy is 0. The key to this is that all energy concepts are relative. And so you want to zoom in enough so that you can work with relative energies in an easy way. For instance, you can pick this line right here as y equals 0. And so that makes sense because that's the floor of the classroom. And so what you're going to find is the delta y is this height right here. And that is an easily measurable height. This is an awful drawing, but basically, like, if I hold something in the air in the classroom, I can take a meter stick, put one end of the meter stick on the ground, and very easily measure the height of that object relative to the ground. When I use this equation, I am communicating how much more gravitational potential energy this ball has than as if it were on the ground. And that's very relevant. Now, to talk about like some poor decision making, I could instead decide that the ground where RMHS is on, in other words, Earth, is 0. And then the only problem with that is when I go to measure the height of it, I have to now include the height of the 2 floors underneath RMHS on the way to the ground. And so it's not as useful. Is it more accurate? I guess so, but I wouldn't really care about that. Everything is relative. So if the object or system that you're studying is in the room with you, then confine all of your energy concepts to the room itself. Make sure that your height that you measure is relative to something that's easy to measure. So when all is said and done, delta y is more or less height above some surface. Now, it doesn't have to be a surface. You are not confined to this statement right here, but you want to think of delta y as height. How high is it off something, maybe the ground, the lab bench? How high is it relative to some other structure is also useful. So there's lots of creativity in here, and you should feel, you should take license to play with this idea that you get to decide where there's no gravitational potential energy. I will say often, if you're not sure what to do, make it the lowest point in your picture. That's the best way. If you're not sure what to do, that's the best thing to do. Okay, so that's gravitational potential energy. The last part of this video, and I'm rambling, so sorry this is going long, is mechanical energy. Mechanical energy is really what we are here to study in this unit. Mechanical energy is the total energy due to motion and I would say like organization or structure. And the like kind of code that I'm speaking in is motion is kinetic energy. Organization is a good placeholder for potential energy. So the variable for mechanical energy is a capital E, and mechanical energy is equal to all of the kinetic energy plus all of the potential energy. And so we have like 3 equations for this lesson today, and you are going to work with them in future lessons. So mechanical energy is the sum of all the kinetic and all the potential. Potential or gravitational potential energy is mass times little g times height. This is essentially weight times height. And then the translational kinetic energy is 1/2 the mass times the speed. And so we'll work with those in another lesson. Thanks.